Alright, in this mini lecture we will wrap up Chapter 9 with some wild, crazy, maybe magical, and incredibly useful new reactions involving organometallics. So, outline-wise, we've already actually seen organometallics in Chapter 19. Remember, this is where we learned how to make Grignards and our organolithiums, our cuprates. But now we're going to revisit those and see what else they can do and learn a few more organometallics. So we know how powerful Grignards and organolithiums are. We know that they're really, really good for reacting with carbonyls. So that, for example, after workup, this would give us a nice tertiary alcohol. It stands to reason, then, that that good carbon nucleophile should react happily with that carbon electrophile to make that new carbon-carbon bond. Similarly, it stands to reason that an organolithium would do that too, right? Boom, boom, new bond, new bond. Yay! Well, not yay. It just doesn't work. It doesn't work well at all. You can get some coupling product, but if you really, really want a new carbon-carbon bond by adding an organometallic to an alkyl halide, the cuprate is your organometallic. Cuprates work quite well at coupling to alkyl halides. So what's particularly nice about cuprates, there's our little happy dance because this works so well. What's so amazing is that these cuprates can do that even in the presence of functional groups that would otherwise be a problem for a Grignard or an organolithium. Furthermore, in cuprate chemistry, when they react with an alkyl halide, this reaction takes place with retention of configuration. So here's an example that illustrates this. Basically, what am I going to do is I'm going to add my cuprate, and it's going to couple right there where my leaving group is. Now you know that if you were trying to add an ethyl magnesium bromide to this particular molecule, you know the only thing that would happen is the negative charge here would just deprotonate that alcohol, and you'd have a dead Grignard and no good reaction. But cuprates works like a charm, and notice that the stereochemistry about the alkene is retained. In other words, the iodine, was on the same side as the CH2OH in the starting material. The ethyl group is on the same side as the CH2OH in the product. So, cuprates couple, they work well. If you want to carry out this reaction in a synthesis, make sure you use the cuprate, not the Grignard, not the organolithium, because they just don't work well. So, what's so special about copper? Well, copper is in, of course, the middle of the periodic table. It is a transition metal, and we are going to see that a whole bunch of these transition metals are really useful, have special properties that are super handy in organic synthesis. Palladium is one of the biggest ones. So, just as we saw this cuprate doing coupling, there are multiple versions of palladium catalyzed coupling. So now, let me underline catalyzed. What we just saw in the cuprate was a stoichiometric coupling reaction, where I need one equivalent of this to couple with, let's make it, I don't know, we'll do that. One equivalent, so if I have 1 mole of the cuprate, I need 1 mole of this, and I will get out of my product that product. Alright? So there's nothing catalytic about cuprates. Palladium catalyzed coupling is specifically that. a catalyzed reaction where you use two different pieces and manage to kind of stick them together magically through the intermediacy of palladium. There's tons of examples. The two that Carty focuses on, and of course it will focus on, are called the Suzuki and the Heck. And what the heck is L, and what are the mechanisms? These are things I'm going to introduce as we go along. These are kind of general new concepts that we have to talk about with respect to organometallic chemistry. So what the heck is L? L stands for ligand, and basically a ligand is something that coordinates to a metal. And it can be all kinds of things. Basically, what it really is something that is a Lewis base. Well, what's a Lewis base? A Lewis base is an electron pair donor. So you could consider a ligand just another example of a base. All right, so they don't participate in the reaction. They're kind of just there for show. They're to keep your metal stable. They don't really play any role, and that's a lie, but we're going to oversimplify, in the reaction. And then mechanism-wise, we're going to really simplify organometallic chemistry and say that there are kind of, and this actually is true, there's really three key reaction elementary steps in organometallic chemistry. They're called oxidative addition, reductive elimination, and we'll see on the next slide, beta hydride elimination. So in a nutshell, oxidative addition happens when you have an organic partner like bromobenzene and a metal that is in its zero valent oxidation state, like, for example, palladium 0. Through the miracles of chemistry, and we don't really talk about the mechanism, but it's kind of like what we see in the Grignard, right? Could be Mg0. Formation of the Grignard reagent is an actual oxidative addition. The metal gets oxidized because in the case of the Grignard, it's now magnesium plus 2, and it's obviously added to the metal. So I have oxidatively added my organic partner to my metal. Okay, so this is a pretty widespread organometallic elementary step. So just again, just to emphasize, we are oxidizing our metal and adding it to an organic partner, typically an aromatic halide or maybe a vinyl halide. All right, what's reductive elimination then? Well, reductive elimination and oxidative addition go hand in hand. So once I have a metal that has oxidatively added an R group, like we just saw, maybe a phenyl group, if it has something else on here, maybe a different R group, it can eliminate those. And that elimination will take place in such a way that it's as if this R double prime swings over and hits R prime and gives a pair of electrons back to metal, back to the whatever M to the plus 2 is. So this gives me this reaction, or this product, and my metal is reduced because it got back that pair of electrons. And obviously I've eliminated two groups that were attached to the metal, R prime and R double prime. So oxidative addition happens to put R groups on the metal. Reductive elimination can take them right back off again. Finally, there's beta hydride elimination, and these are the three elementary steps you're going to see in Chapter 19, the rest of Chapter 19. Basically, what we're looking at here is very, very similar to what we've seen with other elimination reactions. Remember how we would look at Well, let's do E2. E2 will be more valid here. Here's our leaving group. Here's our hydrogen. What we would see would be a base. And we eliminate to make an alkene. It's kind of like that, but not really. What we have is a metal, which has a metal carbon bond. And next door to the metal, so this is alpha, this is beta, is a hydrogen. What's kind of weird is that it's as though the metal is my base. Other than that, it's pretty much the same thing. It slams down here, makes an alkene, and gives the electrons back to my metal. So that gives me a metal hydride and an alkene. Alright, so I'm going to keep these really short. And so this will be the end of this mini lecture. We've just outlined the basic mechanisms. In the next mini lecture, what we'll do is we will go through the specific examples for each of these.